We're on lesson 6 of chapter 3, which asks us to model direct variation. So here we're going to identify and graph direct variation equations. We're going to write and use a direct variation equation, and then we'll solve a real-world problem. Direct variation means that there's a relationship between the x and the y, the input and the output if you're doing a function. So in this case, we would see that when x is 1, y is 20. When x is 2, y is 40. 3, 60, 4, 80. See how this is always 20 times what x is? That's direct variation. There's a constant change between 3, 4, 5, and 6. It's always going up by 20. And you'll notice that direct variation has to be going through the origin. If it traveled through the 2 or the 3 or the 20 or the 40, it would throw the entire relationship off because the ratios would no longer be the same. So you'll see that a great way to find out if something's direct variation or not is to see if it passes through that origin. If it does not, it's not direct variation. So let's think about that here. Determine whether each equation represents direct variation, and if so, identify that constant of variation and graph it. So here we have 2x minus 3y equals 0. So I could subtract 2x from both sides. And that would give me a new equation, which I can write down here. Negative 3y equals negative 2x. Divide both sides by negative 3. And that would give me y equals negative 2 divided by negative 3 would just be 2 over 3, and then make that x. So here's our direct variation equation. There's nothing being added to it, so here's the key. When it's plus 0 or just nothing after it, this is direct variation. Y is always 2/3 of x. When we have plus 8, for example, this would throw it off because then it's no longer 2/3 of x, it's 2/3 of x plus 8. And then it's not always going to be a neat ratio there. Just to show you, if we graph this here, if x was 3, y would be 2/3 of that, so 2. If x was 6, y would be 2/3 of that, so 4. If x was negative 3, y would be negative 2. Negative 6 would be negative 4. And we're going to see that this line, if we're going to go from point to point, does go through that origin nice and perfectly. Let's solve it for this one then. We have negative x plus y equals 4. So to get y by itself, I would add x to both sides. So if we're going to write this out, I'd have y equals x plus 4. And let's see what that would turn out to be. Well, y is always 1 of x, but that plus 4 throws it off. If I draw this on the board, my y-intercept would be 4. And then slope of 1, so 1 and 1, 1 and 1, go backwards. So that relationship of multiplying and dividing is no longer there because it crosses at that positive 4. So 1 and 5, for example, that's 5 times as big. 2 and 6, that's only 3 times as big. See, that's not the same ratio as we had over here. So in this case, we're going to say direct variation. And it's 2/3 for the constant. It's always 2/3 of x. This one we're going to say not direct variation, and there is no constant. Here we actually can use this direct variation graph to write an equation, then find a value for y. So we have negative 1 and 2, and we see that it's direct variation because it goes right through that origin. So what we can do is we can write an equation here. So y equals a, which is the constant, times x. We can find out the constant by plugging in the y and the x here. So 2 equals a times negative 1. Divide both sides by negative 1. So we'd have negative 2 equals a. So a, our constant, is negative 2. So we can actually plug this in now if we find y. So what is y when x equals 30? We would do negative 2 for a times 30. So negative 2 times 30 would be negative 60. So when x is 30, y equals negative 60. And we see that this makes sense. As x becomes positive, we see that y is now in the negatives. And then so as the further along you go along the positives, the y would go pretty far into the negatives here. Let's do a real world problem. The number of tablespoons of sea salt needed in saltwater fish tank varies directly with the gallons of water in the tank. A pet shop owner recommends adding 100 tablespoons of sea salt to a 20-gallon tank. So we have W for water, and we have S for salt. So if we're going to write this out as the equation, we'd have S equals the constant times water. Okay, so S for salt equals the constant times the water. We could plug these numbers in then to find our equation. 100 tablespoons of salt equals the constant times 20 gallons. Then we can divide both sides by 20. Then we find our constant, that would be 5 equals our constant here. So A equals 5. So let's write that equation in for this then. How many tablespoons of salt should be added to a 30-gallon saltwater fish tank? So we have salt equals A times W, right? We found that the constant is 5, so salt equals 5 times, and then 30 gallons of water, so 30. 5 times 30 would be 150. So we would need 150 tablespoons. So all we did is we needed to find the constant first. So we did salt equals the constant times water, plugged in the numbers, find the constant, then apply that constant to the amount of water that it gave us, and that gave us 150 tablespoons.